Welcome to homework.
Okay, here we've got cyclohexanone, and we're reacting it with LDA, following that with ethyl bromide. And we've got two situations, one in which we're doing it at negative 78C, and one in which we're doing it at room temperature. And the question is, what difference will that make for the product? Now, in this particular instance, it's not going to make any difference, right? The difference between the temperatures here is the low temperature will give the kinetic product, the kinetic favored product, whereas the room temperature here will give the thermodynamically favored product. Okay. Uh, that only matters if there is a kinetic product and a thermodynamic product, right? So we're actually going to come back to A and B in a second after looking at C and D, which do have a distinction based on temperature. Okay, so compare this instead to C and D, in which we have methyl cyclohexanone, right? So all of a sudden, we've got options, right? We can deprotonate with the LDA here, or we can deprotonate with the LDA here. Remember what LDA is, lithium diisopropyl amide, if you will. Oops. Okay. It's a strong base, but it's a bulky base, right? Lithium diisopropyl amide is going to prefer, no matter what the situation is, abstracting that proton because this methyl group is not in the way. Okay. But the point is if the temperature is high enough, say at 25 degrees C, and since this uh, reaction is actually an equilibrium, right? Uh, the equilibrium and the shifting back and forth of the products to reactants and reactants to products will eventually favor the more thermodynamically favored product, right? So, what do I mean by thermodynamically favored product? When lithium diisopropyl amide deprotonates uh, this blue proton, the product we eventually get is this. And if we deprotonate on the right hand side, the product we eventually get is this. And recall that the intermediates here for either of these are and right. So the point is that this more highly substituted at the alpha carbon is thermodynamically favored, but it's kinetically hard to get to, right? Because we've got to access this sterically hindered proton. So this is the thermodynamically favored product. Right? And when we've got a high enough temperature, then we can take full advantage of this equilibrium. We can pass back and forth between products and reactants to end up with the highest concentration possible of the more stable product. Whereas at low temperatures, we're under kinetic control and we don't pass back and forth on the equilibrium to give us the highest concentration of the more thermodynamically favored product. We just end up with whatever's the easiest to make because there's not enough energy available to overcome that barrier again and again and again. Right. So for C, right, at low temperatures, this is the answer. And for D, at high temperatures, this is the answer. Okay. But for A and B, it makes no difference, right? There's not a kinetic proton and a thermodynamic proton. They're the same, right? So no matter what, A and B will both give the same product. And that's kind of tricky, right? But this is what you get no matter what. This is the answer to both A and